The main topic in this chapter, and also the last topic for these lectures, is kinematics. Kinematics is really the study of constant acceleration. And the core of kinematics is 4 kinematical formulas. And those are the ones I have written here on the slide. And I've also copied them over into my whiteboard section. So most textbooks will have these 4 formulas. I commonly list them in this order, and will sometimes say, here's the first one, here's the second one, here's the third one, here's the fourth one. I have a few other concepts associated with them, but I'm going to kind of wait till we get into the examples to further elucidate all of those. I do want to note there are sometimes some different notations that are out there. So like one example, if you use delta notation a little bit more liberally, the first kinematic formula, for example, could be stated as delta x is equal to v naught t plus 1/2 at squared. Let me make this t look a little different than a plus here. A didn't turn out well either. I guess my pen's malfunctioning. I don't know. But that's another way. Basically what I did there is I subtracted x naught or x sub 0. I say naught, it's like NaUGHT for it's a fancy word for 0, right? But that's a subscript that I commonly use, and it's pretty common in textbooks, that means initial. But if you subtract initial, then x is really like final position, and it's x minus x initial would really be delta x. It turns out some textbooks will also write these like they'll have an x sub f is equal to x sub I plus v sub it plus 1/2 at squared, where they're using I and f as the subscripts for final and initial, as opposed to like just the number 0 or not and unsubscripted respectively for initial and final. So again, there are these different notations. So like if I were to write the other 3 kind of maybe using this delta notation as just one example of, then I haven't seen this too often, but you could write this, I guess, is that the second one is delta v is equal to at. That kind of relates to the definition of acceleration, really, though, so that one's kind of simple. The second one you could clearly write as delta x is equal to v naught plus v over 2. And we'll probably see in one of the examples here that there's maybe another way of thinking about what this part is for this one. And then the fourth kinematic formula, I usually like to write it like this, although I've seen some sources that will subtract this v naught squared onto the other side. But again, just kind of following this example where I'm making things look differently by using some appropriate deltas to represent final minus initial. The fourth one, I just applied that to the x minus x naught that's in this grouping here to change that into a delta x. And so I just want to show that because definitely as I go through the problems, I may sometimes use, particularly this delta notation, I may use that instead once in a while. I try to stay consistent with my subscripting. Maybe once in a while I could do something different, especially if I want to emphasize initial and final in a way that's sub I and sub f. And there's other parts of this class where I like to use I and f for other things that are outside the scope of kinematics. So it's not always going to be that I'm going to use this kind of convention for initial and final. But again, it's good to be aware. So in that sense, different people, different sources, different texts. You may see this if you look at different stuff, resources out there. You'll see things look slightly differently. What I'm going to do in the examples here is I kind of methodically go through each of these formulas. So I'm going to start out by looking at examples relating to the first formula, and then it'll be the second formula. I think there may be one example that kind of has a couple of questions that appears in one example that go from like, I can't remember if it's second or third or whatever, but basically I'm going through sequentially, and then after I've done some examples where I use just one, I show some examples where maybe you could use more than one in a situation. Sometimes you apply more than one formula to the same situation. Sometimes it's kind of a multi-process situation, because I like to look at these formulas as describing a process. So when I think about a problem, I'm going to look at the problem and conceptualize a process and then figure out how one or more of these formulas might describe that. And again, if you're kind of like thinking right now, like, what the heck do you even mean by that? Can you just answer that question right now? My answer is no, I'm not doing that in this video. Go to the next video and keep going, and you'll hopefully get some answers to that.